Good morning. Welcome to the third industrial seminar series talk in MSSE and UMSEC. It's my pleasure to welcome you to the talk today. We have a double header. We have two of our faculty in programming languages and software engineering giving talks about some interesting and exciting research they are doing. It's my pleasure to first introduce Professor Erik Van Wyk. Erik got his PhD from University of Iowa and did his postdoctoral research at Oxford. His research interests are in languages, programming languages and formalisms. And Erik has done some exciting work and interesting work in terms of extensible and modular languages, where you can take a language like C and extend the language based on your application domain with domain-specific extensions, with syntax and semantics and analysis and so on. And he has some tools and framework built around this. It's my pleasure to welcome Erik to enlighten us on his research. Erik, please take away.
Thank you, Sanjay. So I assume you can hear me and see me and all, and we're ready to go. So
yes,
we can hear you. Let me share.
As you share, I just wanted to make a note that these are open to public too, though it's an MSSE seminar series, and we usually host these lectures recordings on our YouTube channel.
All right. Well, thanks everyone for the invitation to be here. It's a pleasure as always. Sanjay, if there are questions, please feel free to interrupt me. I may not always notice things in the chat, so please just speak up. So,
and I will monitor the chat.
Okay. Yeah, and please, just give me a holler if there's questions I can address. So. Yeah, so what I'd like to talk to you about today, and maybe the first thing we should settle up here, Sanjay, it's like about an hour, is that right, that this goes?
Yeah, we have 3 hours, 8 to 11, 15 really, and we can stop and take a break and then start Matthias' talk a little after 9:30.
Okay,
depending.
Okay. I mean, I can fill 3 hours of language talk if people want, but that's probably not what everybody's after today. So
an hour and a half is nice, I think.
Right. All right. That sounds good.
Hour and a quarter.
Thanks. Right. So what I'd like to talk to you a little bit about is some work we've been doing in my group on extensible programming languages and how one can get some control of the language that you use. We make pretty coarse-grained decisions when we pick a programming language. And so the set of features that are available to us are in that language, and we have very little choice. If I pick Java over C#, over OCaml, over Haskell, each of those languages comes with a set of features, but I can't really tune them to the problem that I'm after. So this is sort of the space we're trying to work in here. And I'll say a few things about, the broader area of programming languages. So this is really an area of study about the design implementation of languages. How do we decide what are good language features? How do we build language features? How do we implement compiler optimizations? There's a whole lot of things that sort of happen in this general space. And I'll say a few things that are sort of on the theoretical side. And these go to how we specify, how we write down what a programming language is. And so if the compiler is our only definition of what the syntax is of a language is and what the meaning of phrases in that language is, that's not a very good place to be, right? We would like to write down some sort of formal notation that describes precisely what the syntactic structure is, precisely what the semantics are in terms of typing of a language, code generation, things of that nature. And we might also be interested in verifying properties of programs and languages. So a language like Java or OCaml or Haskell or what we call type safe. And they come with a particular property that says, if I write a program in one of these languages and the compiler can correctly assign types to all the expressions, so there's no type errors, then we know when we run that program over any input, certain kinds of errors will not happen. Right? And so this is a property of all programs written in a language such as that. And so that's another sort of a piece of sort of verification people do in this area. That's on the theoretical side of things. On the practical side, right, programming languages as a field is also interested in, improving software development. Right, there's all sorts of studies of how many bugs there are in code and how expensive it is to fix these and the problems that they cause. And so on the practical side, we want to make it easier and faster and more efficient to build correct systems. And so part of this that I'm especially interested in is this notion of closing this semantic gap, right? So between what we think of as programmers and what we think our particular solution to a problem is, and how we have to translate that into machine code eventually that will evaluate and execute and solve that particular problem. And so if we can close this semantic gap, that the distance between me and the execution, and even just between what I think and the way I write down the solution in a programming language, if we can close that gap a little bit, right, it makes it easier for us to write correct programs that are fast, things like this, desirable programs. And so that's what I'll sort of try and talk on a little bit here, is this sort of theoretical side and the practical side. And I think, yeah, so it looks like some of my slides are cut off there on the bottom. Let me adjust that a second. Oops, that's not helpful. All right, well, maybe we'll live with missing page numbers at the bottom. So. All right, so on the theoretical side, what I'm mostly interested in is language specifications. How do we write down what a language is, right? What its syntax is, what the underlying structure is. This is what we call our abstract syntax. And then this gives us sort of a bridge to semantics. What does that program mean? What does that assignment statement mean? What does that class mean? And what we're after here are first making sure the things we write are well formed, they're type correct. How do we decide what that means? And then also how we translate this for execution in a way that does it in an efficient way. And then finally, these sort of meta-theoretical properties of specifications. So this notion of type safety is one that we're interested in. So how do we specify that property that programs that have types don't exhibit type errors at runtime? And on the practical side, then we're going to look at something called extensible programming languages, where we make use of these sorts of notions of language specifications. So we don't view languages as sort of big monolithic things, but they become things that programmers can modify and extend and gain some control over. Right. So the way we're going to start this is by looking at some sort of motivating questions, right? And so these questions are listed here, right? And we're asking, can programming languages be constructed from separate modules, right? Each defining an extension to the host language. So instead of thinking of, your programming language as this monolithic thing that comes to you from Oracle or Microsoft, and you have no sort of control over the syntactic structures of that language, right? How can we think of doing this in a modular way? And we're interested in extensions that add new syntax and new semantics. And we want these extensions to be developed independently, so that the same way we do libraries, that I can build a library, someone else builds a library, and a programmer can make use of both of these things without me and the other library writer needing to somehow talk to each other to make sure that these two independently developed libraries are compatible. We want that same sort of notion for language features. All right, and so the idea then is what we're really after is making sure that programmers can sort of take charge of this composition process of building a new language from a collection of extensions, a collection of features that live in an open library that anyone can contribute to. All right. So I think it's maybe clarifies a lot of these things to give you an example of what we're after. So what we're going to consider here is starting with C as a programming language, and we want to add features to it, right? And what we're going to add here are three, right? The first is what we call inductive data types. These are sometimes called algebraic data types. You see these in languages like OCaml or Haskell. Scala has these as sort of a notion of case classes in that language. We also have regular expressions, right? So we might like to have a way to write down regular expressions directly in our language, compile them into efficient code, and to match patterns in strings. And we're also going to look at an extension based on the Silk programming language that gives us some mechanisms for writing parallel programs. So there's a sync, a spawn, and a sync command that we use to sort of spawn processes and synchronize them. And what we're going to do is try and count the number of nodes in a tree that contain a string that matches a particular regular expression. So this is a program that does that. And the colors here are meant to indicate that things in black are plain C code. So your first glance at this, you should say, oh, it looks like C. I see a type def. I see stars indicating pointers. It's C code. Well, it essentially is C code, but the colored parts are syntax introduced by those three extensions we just discussed. So in blue is the inductive data type syntax. And so we're saying here, I want a new data type, right, called tree. And it has two constructors, right? There are fork versions of trees and leaf versions of trees. And so, you know, you could think of these roughly as tree as an abstract type and fork and leaf are concrete classes implementing that type. But we don't really think of those terms in functional languages or in thinking of inductive types. We have a type called tree, and there's two ways to make trees. I either create a tree with the leaf constructor by providing it with a string, or I create a new tree that's using the fork constructor that has two subtrees, and then a string as the third element of this kind of tree. And what we'd like to do is call this function count matches given a tree. And we want to count how many strings in this tree match a particular regular expression. And so this is a silk function, right? So this is syntax introduced by a separate extension to the language. It gives us access to the silk constructs. And so when we match on a tree, right? So we look at a tree and we want to know, is it a leaf tree or is it a fork tree? And in the case where it's a fork, all right, we pattern match on that. We pattern match on T, recognize it matches this pattern. And now we can reference T1, T2, and the string. And so what do we want to do? Well, we want to make some recursive calls to count the matches in T1 and T2, all right? But we spawn these so they run in parallel. After those two are spawned, the main thread here continues on, and it checks, does the string at this node match this regular expression? And so what we've introduced here is some syntax for regular expression literals and a new operator that matches a string against a regular expression, right, in green. And once this is done, we sync, so we wait for the two other processes to finish, and then we can add up those results. In the case that it's a leaf, well, we have a mechanism here where we actually check the string against that regular expression. And if it matches, we return 1. Otherwise, in all cases, matching the wildcard, we return 0. Right, so the idea here is that our programmer wants to write a program to solve this funny little problem and likes to use inductive data types. They've seen those in other languages. Silk is a nice way to organize parallel computation, and there's some regular expression work that has to be done. And so as a programmer, I'd like to sort of use all these features in the program that I'm writing in this extensible implementation of C. So how does this begin to work, right? If you buy the story that, oh, this could be sort of useful, I can now customize my language to the problem I have at hand. How do we go about doing this? Well, the big picture here is a programmer essentially picks these 4 extensions, right? We saw the first 3, and the 4th one here is actually the one that combines algebraic data types and regular expressions to use them in patterns. But essentially, there's a program where I say, all right, I'm going to use ABLEC. This is our C specification, and this collection of extensions. And what I do is give these to a tool called Silver that combines the specifications of these languages and language features and builds a compiler out of them. So if you're familiar with tools like Yak and Lex and other compiler generation systems, it's sort of in that ballpark that we take language specifications, combine them, and build a compiler. And so we take that little program we had before, this PTS parallel tree search.xc, so XC is sort of extended C code, and we give it to the C preprocessor, inline all our includes and such. This goes to our ABLEC compiler, the parallel tree search compiler we've just generated, and we get a plain C program. All right, so we're translating all that extended features, all that inductive data types and silk spawns and sinks and regular expressions, all gets translated down to plain C code. We compile it with a regular compiler and run it. And the important part is that this compiler that we generate, it's a lot more than a macro processor, right? So you may look at this and go, oh, there's new syntax. It's some fancy version of macros that generate C code, and that's what they do. It's a little more involved in that, right? So what this generated compiler has to do is scan the text, chopping up the characters in that file into essentially words, identifying white space, removing comments, these sorts of things. Once we've done that, we need to recognize the syntactic structure, right? So this means we need to parse the program, generate a tree representation of it, which we call the abstract syntax tree. On this abstract syntax tree representation, we can do things like type checking, optimizations, and then finally generate plain C code out of this, right? So one of the important ones here is type checking, right? Any errors that I make as a programmer in that extended program, I would like to get error messages about mismatches in my patterns on inductive types, an incorrectly written regular expression. I want error messages in terms of the program I've written. I don't want error messages coming out of that C programmer, right? If GCC reports error messages, then we have a problem. Then we get error messages that are coming from the code the compiler generated, that the tool generated, not the code that the programmer wrote. So that's our aim, right? And so how do we begin to do such a thing, right? So we have a few requirements, right? What we want to see here is that this process should be automatic and verifiable or reliable, in that as the programmer picks these extensions, that composition process is just a matter of selecting the extensions. The composition is done automatically. And it should be verifiable in the sense that we know it should work, that the generation process doesn't give me an ill-formed specification, sorry, the composition process doesn't give me an ill-formed specification of the language. All right, so if I have different language features and they introduce some ambiguity when I compose them, that would be a problem. And that's what we're trying to avoid with this notion of verifiable. Right, we want to be able to generate language tools, right? So generate a compiler or an interpreter out of these specifications and do this efficiently. And importantly, we want language features as extensions to give us new syntax and new semantics, right? So the new syntax we saw on that slide with that example, but new semantics here are a few things, right? So if we pop back to this slide here, right, we would like to make sure that in this match, I've actually matched against all possible patterns, right? So my patterns here of fork and leaf and underscore cover all possible versions of trees. I'm not missing any constructors for trees in this process. So we want to do error checking on this. The other thing we want to do is think, what does a silk extension, a silk function translate to? Well, the silk runtime is actually quite sophisticated. This was developed years ago at MIT. It found its way into Intel C compilers for a while. And essentially what we do is a silk function turns into a fast clone of the function and a slow clone of the function. And it's not so important here, but the point is that these two versions of the function, two clones, behave slightly differently with the parallel programming runtime to generate efficient parallel code so that we can spawn lots of threads and we don't, well, they're not actually threads, they're very small tasks. And we want to avoid a lot of parallel programming overhead. So this is what the silk language did well. And so the semantics of the silk function are to process the body of the function and generate these two variants, the two clones of that function. So that's what we're sort of thinking about in terms of semantics, is we have to do some analysis or some code generation over the new syntax that has been introduced. And so there's a few challenges we have to consider here, right? One is concrete syntax, right? How do we ensure that the parser that we generate for this composed language can actually recognize the syntactic structure in a string, that the language we've created is not ambiguous, that it falls within a particular class of grammars that we can generate efficient parsers for. And then also, you know, this notion of abstract syntax and its semantics. How do we do that? So these are the two things I'll talk a little bit about here in the next collection of slides. Are there any questions before we move forward here? All right. So how do we do this, right? How do we think we're going to build some system that composes language extension specifications and generates a custom compiler for the task we have at hand? All right. Well, let's look at concrete syntax. So the first thing we do, concrete syntax is usually broken up into two pieces, right? One of them is the lexical syntax. And the aim here is to identify the words, if you will, in our program. So we want to drop comments. We want to drop white space unless it's a white space significant language, then we may use the white space to identify structure. But otherwise, we're kind of chopping up a sequence of characters into a sequence of words or tokens that can be used in the next phase of our compiler. And so this is often done by specifying categories of words, the tokens, and a regular expression that matches, that identifies that particular category. Right? So an identifier, we might think this is a good attempt at a regular expression for identifiers. It says they have to begin with a lowercase or an uppercase letter. And followed that, there can be 0 or more. That's what star gives us, right? 0 or more letters, digits, spaces, or underscores, right? And integer literal is just 1 or more digits between 0 and 9. The while terminal symbol, the while keyword is just the string WHILE. And we want to recognize that there's some lexical precedence here, that if I see WHILE, that's the while terminal symbol. We don't want to recognize that as an identifier. So we have some notion of lexical precedence here to say that keywords take precedence over identifiers. We may have operators like plus, etc. So we write down these regular expressions for the terms, the tokens, the words in our language. We do this for the terms that are introduced by a language extension. And so the composition of this is sort of trivial in that it's just a bunch of regular expressions. Generating a scanner for this is not a difficult process. And the composition is straightforward, but we have to worry about resulting ambiguities, right? That two extensions may introduce the same term as part of their sublanguage. How do we process something like that? So let's look at a few examples of ambiguities in language, in lexical syntax. So these are the things we want to avoid. Right, so one extension we might add, a sort of canonical one in this area, is embedding SQL into a language. Right, so we may say, well, all right, well, I'm going to have an integer called select, And I have some new syntax that, given a particular connection to a database, I want to run a query and return some results in RS. And so this query is a little bit of SQL code, right? And so the thing here we see is a select here and select there. And inside the query, right, this one we want to recognize as the select keyword and part of the language of SQL, part of the language of this particular extension. Where the one above, we may say, well, that's in a different context. It's not inside this query construct, so that's just a regular variable. We see this again in the same extensions, thinking about the term table. All right, so in setting up a connection to a database, I may identify the file that contains the database and then write down the schema so that we can type check the queries that are going to occur in this program. We'd like to verify this schema matches what's actually in that database. But we'd like to write that down so we see it here and it's part of sort of a checked documentation in a program like this. So we have the keyword table. We want to recognize it as such inside this schema spec. But there's another extension we might add that builds tables that are sort of disjunctive normal form representations for complex Boolean expressions. And the way we read these is to say, well, I have a couple conditions that a level is less than 20 and a height is greater than 40. And this table representation is going to be true or false, depending on the values of these two expressions, these Boolean expressions. And the way this works is that if the first one is true and the second one is false, then this entire expression evaluates to true. Or it could be that the first one is false and we don't care about the second one. In that case, we'd also like to have this expression evaluate to true. And so this is this is something you see in specification languages for avionics. I think good old RSML had this for a while, where we first saw this anyway. And so now again, I have this ambiguity between these two notions of tables. What about star? I have multiplication. I have a star inside my regular expressions. How do I distinguish these things? I may have a bit shift operator, and I have two greater thans at the end of a type. How do I distinguish those? They really should be seen as different symbols. So what we're going to do is tie together the lexical syntax where we see these ambiguities, and we're wondering how are these ambiguities going to be resolved. We want to tie the lexical syntax to the phrase syntax, the context-free syntax that we get by writing a grammar, right? So the first phase of concrete syntax is the lexical part we've seen and the challenges there. The second part is the structural syntax, where we want to say, well, what is the structure of the language that we are designing or have designed? And we do this using context-free grammars. Right, and context-free grammars essentially give us patterns for constructing derivations of programs, and these are written as productions, right? So this first production here says that, well, one way to make an expression is to start with an expression, follow it by a plus sign, and follow that by another expression. Right? We'd have another rule that says an expression can be an integer constant. So we'd have expression on the left-hand side of this funny symbol and integer constant on the right-hand side as sort of the body of that production. What about statements, right? We have languages that have expressions and statements. A statement can be a while keyword followed by an expression, followed by the do keyword, followed by a statement. And so grammars are essentially collections of these non-terminal symbols like expression and statement, and productions like we see here. And again, the composition of these kinds of specifications is trivial, but the problem is they may result in ambiguities. And so our aim here is to sort of constrain the way we write specifications for language extensions such that these ambiguities cannot occur. All right, so, one example here, if this is my grammar, where I have multiplication and addition productions. An expression is an expression plus an expression, or it's an expression multiplied by an expression. You know, how do we interpret something like this? 1 plus 2 times 3. Well, we all know that multiplication has precedence over addition, and so we want to interpret it in a specific way. Well, the grammar that's written here is ambiguous. The grammar does not encode that notion of precedence. And so we may have to rewrite the grammar to explicitly encode this precedence of multiplication over addition. We may be able to give some other indications of how to make this choice, but this is what we mean by an ambiguity, that there's a phrase and we can sort of derive that phrase in 2 ways, 2 or more ways. And this would give us 2 or more different representations of the same text. And those different representations may have different meanings, and that's what we're trying to avoid here. So how do we do this, right? There's a couple things that's going to happen here. We're going to introduce a notion of context-aware lexical syntax. And what this is going to do is resolve those ambiguities we saw before. And it makes it likely that these ambiguities do not occur. And then after that, we're going to give a guarantee that we can now ensure these ambiguities do not occur. Right? So the first one is a particular way to interpret specifications. And the second one is an analysis that may reject certain specifications that an extension writer develops and says, no, the way you've done this extension doesn't pass this analysis, and it may allow ambiguities to creep in. So let's look at the first one here, which is context-aware lexical syntax. Right, so this is, you know, kind of the compiler writer, compiler generator concerns here. How do I avoid these ambiguities, and what's the process for doing that? And so we saw the word, you know, SQL in the SQL extension. We had a select keyword and a table keyword, and we'd like to think that select as an SQL keyword only occurs inside SQL queries. It doesn't occur in other parts of my programs. It doesn't occur where there's an inductive data type. It doesn't occur in the middle of a regular expression. It only occurs in certain places. Same with the table keyword, right? And our greater than symbol, right, is valid in type expressions to close off a parameterized type. But we'd like to say right bit shift, that's not a valid thing to see in a type expression. And so seeing 2 poorly drawn greater than signs in a type expression would not be valid, and we would not then sort of recognize a bit shift operator in that context. And so what we're doing here is making sure that the lexical syntax is interpreted, right, in the context in which we expect to see these kinds of symbols. And so essentially what we do is change how scanners and parsers work. So traditionally, a scanner would take in the input file of your program, that sequence of characters, and chop it up into tokens and give that list of tokens to the parser, which then proceeds to build a tree and do some semantic analysis. What we're going to do in context-aware scanning is change that communication. So instead of being this sort of one-way communication that the scanner does its work and, you know, finishes, gives the list of tokens to the parser, we want these 2 components to talk back and forth to each other, right? And we want the scanner, essentially the parser drives the process to ask the scanner, I want a new token. And when it asks for a token, it's going to tell the scanner, I'm in a particular position in this program where only certain things are valid. So only return to me, the parser, valid, syntactically valid tokens. Don't give me a bit shift operator if I'm in the middle of a type expression, right? Don't give me a SQL select keyword if I'm in the middle of a regular expression. And so this is we do this using something called LR parsing. So how does the parser work? Well, there's a category of grammars and a parsing technique, this notion of LR parsing, that essentially reads tokens one at a time, shifts them onto a stack to keep track of them, replaces symbols on the stack with non-terminals when we see an expression plus an expression that sits on the stack, and we want to replace it by just expression to indicate that we've kind of reduced 1 plus 2 into a single expression. And so the way these kinds of parsers work is that any particular state, right, there's essentially a finite automata inside the parser. And at any particular state, what to do for each terminal, each symbol in the language, right? We can either shift that terminal onto the stack. It may indicate a particular reduce action. It may indicate that we should accept this string as valid in the language. Or there'd be no action for a symbol. And that's a syntax error, because if we see that symbol at this point in the parsing process, that's a syntax error, right? So there's no action to take for those. And so what we're going to do is essentially in a particular state of the parser, we identify what are valid things to see, right? The valid things that can come from the scanner are only those that have these actions in their entries in the parse table or in the automata representation for this particular point. And so when the parser says, I want a new symbol, it has a way to tell the scanner, but it better be one of these valid symbols. Otherwise, I don't want to see it, right? And what that means is when the scanner sees, these 6 letters in sequence, right? The parser will tell it, I'm in a context where I want you to give me a select terminal, or I'm in a context where an identifier is valid. And it does this based on the structure of the syntax, what is in this, the LR parser state to see what do we do, accept, reduce, or shift a particular symbol. And it lets the scanner sort of be a lot smarter and return only the symbols that are relevant in a particular location. Right. And so that's what lets us take these language specifications that are developed independently and, combine them, which is a straightforward process, but now interpret them in a way that these ambiguities are much less likely to occur. All right. So this is sort of where we get to this point, is that now we have a system, we have a mechanism for interpreting concrete syntax specifications that ambiguities are unlikely. But unlikely is not good enough, right? We would like to have a guarantee that things work out well. So how do we guarantee this? Well, there's a particular analysis that does this. And essentially it is done in such a way that what we're after is this is our goal, right? That I have a grammar for a host language. I have the grammar specifications for a collection of extensions. I merge them together and I get the resulting composed language. And we want this composed language to be deterministic, right? So deterministic is the term we use to mean there's no ambiguity. So we want this as our guarantee. That composed language is deterministic. How do we get this guarantee? Well, we get it, and this is what's important, by looking at each of these extensions individually, right? We say for every I between 1 and n, right? For every one of these extensions, if they have a certain property independent of the others, this gives us a property about the composition of them. So if the host language and extension I are what we call composable, they satisfy some properties we'll talk about in a second, and the composition is deterministic, then we know the composition of all of them is going to be deterministic. And so is composable is this analysis that checks that every extension that is added, it begins what we call a marking token. So a marking terminal. So match is a marking terminal, silk, spawn, sync. These were marking terminals that said, okay, we're shifting into a new context in which a sublanguage is now the language that we're parsing, right? So the SQL extension makes use of the use marking terminal. I say use, a connection, and query, and then a bunch of SQL. It's seeing that use keyword that says, okay, now I'm shifting, the parser is shifting into a phase where we're starting to recognize SQL code instead of C code. So we need a marking token on our terminal symbols. There's a notion of follow sets in language definitions. So what is valid after an expression, right? What symbols can follow an expression? Well, in a language like C, semicolons can follow an expression. right? But we don't think, and so that's fine. A plus can follow expressions in that I have an expression plus and then another expression. And so one of the restrictions of this analysis is that new extensions do not add new symbols to follow sets of host language non-terminals. So I can't say I have a new symbol in my extension and it comes after expressions. This is one of the restrictions we have. And there's a few other minor ones that are not so important. But the important thing here is that it leads to sort of a partitioning of the LR automata that drives the parsing process. And so what these two images here are meant to indicate, and there's sort of a lot going on here, is that the parsing automata is a finite state automata. We see symbols, we recognize phrases, and we sort of bounce around between states. And what we want to do is partition these states in such a way that in certain subgrammar or subgraphs, we know we're working on SQL, we know we're working on a regular expression, we know we're parsing an inductive data type definition. And so with one extension, we end up having a bunch of states that were there only related to host language constructs. And then we have some new states that are related to parsing the extension that we've added, the phrases in that extension. And there's some sort of moving back and forth between these states in the process. All right, when I add two extensions, I still want to see the same host language states, that they're unchanged. And I'd like to see that somehow the communication between two different extensions happens in a regulated way. And what this means is that these two clouds here are not intertwined in such a way that we get language ambiguities. And so by doing this, we then have a strong guarantee that as a programmer, I can, essentially collect extensions out of this open library, download them from the internet. I have the extensions I want. They're developed independently. And I sort of just throw these extension specs to my compiler generator, and it builds me a compiler, and I know it's going to work. Right? I know that there's no ambiguities in the language. And this is something that we've been able to pull off. This was a number of years ago that gives us a strong guarantee for these sorts of things.
A quick question, Eric.
Yeah, please.
So all this is in practice achieved with the existing tools for LR parsing like YAC and Lex?
No.
Okay.
No. So this is all achieved with our parser and scanner generator. Mm-hmm. There's a tool called Copper. It's similar in nature to Lex and YAC, right? That what we've done is sort of taken Lex and YAC and modified them to behave like this, right? This is Lex here and this is YAC there, and they communicate in this one direction only.
One direction, yeah.
And so the tools we've developed then are designed that they use the same ideas of LR parsing and regular expressions for lexical syntax. And a lot of the algorithms are very similar, right? But by giving this sort of communication between the two, we have to change how the parser asks for tokens from the scanner. We have to change how the scanner behaves, that it respects this sort of restrictions that are imposed upon it to say, well, when you're ready to read a bunch of characters and identify them, you have to be constrained to recognize only the valid ones, not invalid ones at that particular point in the parsing. All right, where up here, the parser, the scanner, in a traditional sense, has no notion of context. All right, it just recognizes the same symbols the same way, no matter where it is in the process.
How you were having SQL in your code is really cool because that's familiar with Apex code, how you can do SQL queries. So I think that's a really powerful thing to be able to do that and have those multiple languages together. So it's really cool.
Thanks. Yeah, I think it makes life a lot easier when you can sort of write down your queries directly in your code, and they're not in between double quotes to shoot them off to a server. And the server then says, hey, you sent me an ill-formed query. All the sort of type checking and syntactic checking happens when I compile my program. It doesn't happen at runtime when the query gets sent off to some server in a string or something. So yeah, these are things I think, you know, I don't know, I kind of harken back to this example here. Now it's a little marked up, but the languages here are not terribly rich, right? I mean, the richest one, I suppose, is the data type one here, where we're introducing new data types, but it gives you quite a bit of flexibility that I can, you know, really grow the language to have the features I want for the problems I'm interested in. All right. All right, so there's a little more about there is a caveat to the marking terminals restrictions for this composability analysis, right? That, you know, we saw match as part of the inductive data type extension, but my regular expression extension could have introduced syntax like this. It says match a string with a regular expression, and we then have to distinguish match and match as being two different terminal symbols, two symbols that are from different extensions, but they have the same regular expression. And so this is one that the analysis does not check and cannot check, but it's a sort of ambiguity that's easily resolved by the programmer, essentially by, there's a facility in the tools to sort of indicate, well, if I write match, which one do I mean? Do I mean the regular expression match, or do I mean the inductive data type match? And so these are called transparent prefixes, but essentially it's a matter of giving sort of the fully qualified name to a symbol. It's a bit like Java. If I have two packages that introduce a class of the same name, I need to use the package name to distinguish those. It's not unlike what we have to do here. So that's the only sort of caveat to that analysis. All right, so that's what context-aware lexical syntax is. It gives us this mechanism for interpreting letters in the file and identifying them as terms based on the context in which those terms appear. All right, so this is really the only approach that lets us do such a thing. There's actually more applications for this. It's not only extensible programming languages, which is kind of an esoteric area. All right, it also makes just writing grammars themselves a lot easier. So this issue of the bit shift operator, right? If I don't have context-aware scanning, right, I have to write a production like this that recognizes a type as a type name, less than, a type, and greater than. And I also have to clutter up my specification by saying a type can also be an identifier followed by a less than, followed by an identifier, followed by a less than, followed by a type, and then the right bit shift operator. So this sort of thing also just cleans up the grammars we have to write, because we can avoid this sort of contextual problems that traditional scanners have. This also leads to much better highlighting, right? So the Atom editor makes use of our context-aware scanning work to give you sort of better highlighting, so that we know that if I write a type, I'd like to recognize, you know, these less than or greater than symbols in a type expression. I'd like to see those in a different color than my bit shift operators, for instance. And so Atom and VS Code have a plugin for this approach that, you know, essentially give us highlighting that is much more meaningful than if we use a traditional regular expression based approach to that problem. All right, so that's sort of how we go from a file with a bunch of text into a tree representation that we then can begin doing some sort of semantic analysis on. So I'll say a few words here about attribute grammars. This is the mechanism we use for type checking, generating the C code that comes out of the back of ABLEC, these sorts of things. And an attribute grammar is essentially a context-free grammar and a mechanism to attribute nodes in a syntax tree with semantic information. So I think I may just blow past the sort of formalities here and ask us to consider a simple language that is expressions over Boolean values. So we have true and false constants, we have an or operator, and we have a let construct that lets us introduce names and then use the values bound to that name somewhere in our expression. All right, so if we think of how do I build a scanner and a parser for this, you may have some ideas about that after the previous slides. Now we want to think about how do we do type checking on a phrase of this form. And so before you run away screaming looking at this code, we'll just sort of walk through this slowly and see what the components are. But what we're doing is identifying this as a specification. It's a grammar for this Boolean host language. We have a couple non-terminals. So these are like the types of nodes we'll see in the tree representation. So there's a root node that is always at the top, which is just a little bookkeeping work. And then we have expressions. And so what we're going to do is decorate expressions with semantic information, right? We're going to decorate nodes with a PP attribute. This is sort of a pretty print attribute of type string. We're going to compute the value on expressions. So we have a val attribute on tree nodes, and we have an environment attribute that maps names to their values. And so you may think, a rough approximation is that nodes can be represented as records or structures or objects. And these attributes are essentially fields on those structures. And we want to assign values into those fields to indicate the type or the value of an expression. And we read values out of those fields in computing attributes for other nodes in the tree. So we have a production for a root that says a root can derive or is just an expression. But let's look at the one for lets, right? So that's that expression we saw on the earlier slide. And what we want to say is that a let is an expression named E, and it consists of three things in the abstract: the name we're introducing, the defining expression, and the body of the let. And if I wanted to turn this back into a string, I can write an attribute equation that says, well, on a let E, what's the pretty print attribute? Well, it's let concatenated to the name, concatenated to an equal sign, concatenated to the pretty print attribute out of the first expression, and carry on from there. What's the value of a let expression? Well, that comes out of the body of the let expression. Well, how do we compute the value on a body? Well, the body needs to know what's the environment in which it's going to look up values of identifiers. And we have to extend the environment with the new name, and the new value, so that it can look those things up, the ones introduced by this let. We have similar productions for ORs. All right, here we're sort of taking that environment and passing it down the tree, right? So some information here propagates up the syntactic tree, and other information propagates down, bringing contextual information down the tree. And so the environment is an example of this kind of contextual information that says, all right, the left and the right children of an OR, right, they evaluate in the same environment as the one that the entire expression is evaluating. And when we get to a reference of a name, right, so when an expression is just a name, what do we want to do? What's the value? Well, we're going to look up that name in the environment. And if we find it, we have a value. Otherwise, well, we don't really want to return false here. Maybe we want to kind of blow things up and raise an exception, or prevent this entirely with a static check earlier. So attribute grammars. So when you look at this, this is silver code, right? This is the attribute grammar system we've built. And choosing the syntax for these specifications is, we thought a little bit about this, but we made one very fundamental mistake here. And that is, if you look at this code, the things between curly braces, right? Most of us would look at this and go, oh, it looks like C code, or it looks like Java code. It's in between curly braces. There's assignment statements followed by semicolons. we're obviously just going to evaluate these in sequence to compute these values. And so, but that's not at all how this works, right? We essentially designed syntax for this thing that gives people the completely wrong intuition about how it evaluates. So how we solve all these equations is what I want to say something about briefly next. And it kind of works this way, that here's a representation of that phrase, right, as a tree. And each of the nodes in this tree has a spot for the attributes that we want to compute, right? We would like to know the value of the let expression. We'd like to know the pretty print of a let expression. We need to propagate an environment down the tree, so when we get to our reference here, we can look up n and know what the value of n is. And so this process begins, right, by asking the root for its pretty print value. And so when we have a sort of dot inside the circle here, this indicates that we are in the midst of computing that attribute for root. So we ask root, what is your value of your pretty print attribute? We find the equation for that. We saw these equations on the previous slides. And root says, oh, well, I need to use the pretty print of my sub-expression, which is a let. And the let as says, well, I need to use the string n. I want the pretty print of my first expression. We compute that. I ask for the pretty print off the or. Or says, all right, I need the pretty print off my false and reference nodes. We compute those, and then this information kind of flows back up the tree. So it's a bit of a recursive process that we kind of expand the recursion down the tree and back up as we need things. Value is a little different. If we ask for value, well, root asks for the value off the let asks for the value off its body, right? So whatever the value of that or expression is, that's the value of the let expression. So we go ask it or for its value. It asks its first child for its value, which is false. It asks the second child, this reference, that then says, oh, you know, I need to know what the environment is. And so it asks for the environment, right? Its environment comes from its parent, which comes from the let above, right? That was the name. We see the equation there, that the environment for the body is essentially adding to the environment of the let, the current name and binding value that we're needing. All right, so we ask, all right, go the right direction here. So the or then says, I need this information, all right? The let says, oh, you need the value off that true node, so we compute that. We then can get the environment coming from above. We get that. And I can combine those two things to then give the environment to the or construct, which passes it down to its child, which then can look up its value inside the environment, and we can propagate this value back up the tree. So that's essentially how attribute grammars work, is a sort of lazy evaluation of these equations to fill in the fields, as it were, the attributes on the nodes of this tree. And so specifications like these are sort of easy to compose, because if I add new syntax, I just need to add a new production in an extension. And so the composition of attribute grammar specifications is also pretty straightforward. But we have a concern that the equations are going to be there that we need. So let's pop past this one. And then I'll just say a few more things here about this process. Right, is we add new syntax. Right, so one thing we can do with extensions is add new syntax. So we may add an implication operator to our little language, right? So it's going to pretty print itself with the equals greater than to say, oh, this is implication. Does the first expression L imply the second expression R? And so we may define the pretty print attribute for that. This is a bit what happens with the match expressions we saw in the C code before. But I add a new production in a different grammar for this extension, adds new syntax. We might also add new analyses, right? So we may add a second grammar. This should be an A here. a second grammar called errors. And what it's going to do is do a new analysis over existing code, right? And so we're going to introduce a new attribute called errors. Errors occurs on root nodes and expression nodes. And we're going to write an aspect production. It's a bit like aspect-oriented programming, if you remember that idea. That says, all right, I know there's a production named OR in the host language. We want to add a new equation to that set of equations for the OR production. And this equation is going to do something to compute error messages by propagating error messages from the children. And maybe we want to check that L and R are both Boolean typed expressions. So errors is a list of messages that we want to propagate up. And so the question then is, like, how do all these things come together, right? These are all, attribute grammars are collections of productions. Productions have collections of equations. And so the composition of this is just sort of a piecewise composition of all the equations and all the productions. And it's pretty straightforward. But we have a particular problem, which is, how do we compute error messages, which come from one extension, on the implies production, which comes from another extension? So how do we sort of put these things together, right? Our aim here is that two extensions can be added. They can not know about each other, and they should work together. But one extension is adding new syntax. The other extension is adding new analyses, right? So we're adding implies as a syntax, piece of syntax, and error checking as a new analysis. And so what we do is we have this notion called forwarding. And when I introduce new syntax, like this implication, I can define some attributes explicitly, but I also want to indicate, what do I translate to? What is this new feature in the language? How does it translate into the host language? And here we're going to write down a little expression that says, all right, implication is really OR, where we negate the first child L and take the disjunction of that with the second child R. All right, so this is not just a template. We can write any expression here to generate a complicated tree. We certainly do that for the silk extension and the pattern matching, where we need to take those inductive data types and turn them into what? We turn them into structures and pointers and unions, and it's a big mess of those structures in C. And so it's a code generation that's done with this forwarding notion. Yeah, it can be complicated business that happens here. But in this case, it's just a simple expansion. And so now if we ask implies for its pretty print attribute, right, it knows how to do that. It gave us explicit equations for computing pretty print, this host language analysis that it knew about. All right, but if we ask implies, what are your errors, right? Well, implies is going to say, I don't know what you're talking about. I don't know what errors are. This is something introduced by someone else, and the implies extension has no knowledge of this error checking attribute. So when we ask implies for its errors attribute, right, it says, I don't know. Why don't you ask what I translate to? And so we construct that tree, and then we ask over there, or what is errors? And OR knows how to compute errors because the error checking extension knows about all the host language constructs and provides explicit definitions on all the host language constructs. So the error checking over here happens as we would expect. Maybe it needs the environment to do some error checking on references, right? And we finally say, all right, we've computed the errors on our OR construct. And now we just automatically copy that over to implication, right? So the error messages on implication are the same as the error messages on the OR construct. And so this demonstrates how forwarding works, how we can sort of combine analyses from one extension with syntax from another extension. In practice, however, error checking is often something we do in the host language so that we report error messages on extensions instead of what they translate to. But this gives us an example of what this mechanism is and how this works.
Question.
Yeah.
So is this forwarding always sound? Like when I add new analysis, is it going to be sound?
Is it, well, yes. So, are you asking, do I always have equations to compute the values we need?
Um, you will have equations because there is something in the host language because that it's forwarded to. But the meaning of that analysis depends on, I mean, isn't there some dependency on forwarding to the right thing, if you will, right? Like, is that dependent on the analysis or is it independent of the analysis that we are going to add later? Because I don't know what analysis someone else would add at a later point.
Right. So essentially what the implies extension is doing is saying, I'm semantically equivalent to this construct in the host language. And so any analysis that implies doesn't know how to do will take place on its translation into the host language. And there we can have guarantees that that analysis will complete, right? We may have questions, well, does it give me an answer that I want, right? Well, for errors here, we said, well, now I have the problem that I computed errors on the OR construct. And this might not be the most accurate error messages that I'd like to have, but I will always get an answer for this analysis. So when the analyses are things sort of more along the lines of, a security analysis, the checking information flow that comes as an extension, a translation to a different target language, right? So if I want to translate this to a different architecture, right? I got a new Mac and it runs on ARM processors now. I need to translate to ARM machine code instead of x86, right? Then, those sort of like Is that getting to your question, or?
Yes. My connection is a bit shaky. So the follow-up that I had is it always the case then we should always have some forwarding when we add an extension because we don't know someone else is going to add some analysis at the future?
Exactly. So when I introduce a production that has a host language non-terminal on the left, I have to have one of these forwards phrases, because I'm introducing new syntax that slots into the tree in the same place other expressions would fit, and thus I need to have a translation into the host language. I'm introducing a new version of a host language construct, and thus I need this translation.
Thank you.
Yeah. We have a modular well-definedness analysis here too. So this is important to check that all the equations are there. This is a little more complicated than just checking that if an attribute decorates a node, there's an equation for it. But there's still a notion of well-definedness in attribute grammars that says if I try and decorate a tree or compute attributes on it, I will always have the equations that I need. And this analysis has the same sort of shape as what we've seen before, that I can analyze each extension individually. And if all the individual extensions pass the analysis, right, then I know I have a global property on any combination of those independently developed language extensions. Yeah, I think I rearranged a few things here. We haven't talked about the no leaks extension. This is a security analysis to make sure that information in variables that are labeled as private never flow into or affect variables labeled as public, right? So a password may be labeled as private, and this should never sort of flow to standard output. It should never flow into variables that are labeled as public. And this is an analysis that might come in as an extension as well, that we would do on some extensions explicitly that define the equations, and then others sort of implicitly on the constructs that they translate into. All right. So the last piece of this, I think I'm going to take a quick pass on, since we're already over the hour here by a bit. And this is this question of modular meta theory, where I'll just say a little bit about what this means, in that these analyses we've talked about before they don't tell us that our compiler gives us the right answer, right? They're not sort of I can provide equations in an extension that do wrong things and break properties of my languages, right? So if we're interested in this notion of type soundness, right, I may have gone to some work as a host language designer to prove that the language I've specified is type safe, right? No, if there are types for expressions, there's no type errors, then the evaluation will never have a type error at runtime. I want to make sure that an extension that comes along later doesn't break this property. Likewise, extensions may introduce meta-theoretic properties that the security flow analysis may want to indicate certain properties that it behaves as expected and that those private variables never affect values in public variables. And we don't want some other extension to come along and define equations in such a way that invalidate those properties we maybe worked very hard to prove to be true. So how we go about this sort of modular meta theory is sort of ongoing work. It's similar in structure to the other modular analyses that we want to somehow tease apart these specifications in a way, or these extensions in a way that properties that hold on an extension and the host language in isolation, just those two, that those properties continue to hold when we add more extensions. And so there's some ways we think of how attributes have to behave related to one another that let us move in this direction. But this is ongoing work. So I'll sort of skip some of the details here that are not so important. But the common thread in a lot of this is that we want to be able to write down language specifications, so language features in a modular and composable way so that they can be done independently, right? So experts in the field of databases can build a SQL language extension. Functional programming advocates can build an extension for inductive data types. And as a programmer, I can pick and choose the extensions I want to use, give them to my compiler generation tools that then build me a compiler that I know will work for these features that I'm after. That's our big goal here. And with that, I'll say thanks very much. Of course, I need to thank I have a lot of students who've done a lot of great work on here. Most of them many of them are listed below. But if you have questions, I'd be happy to answer questions or chat about this a little bit. So.
Thank you, Eric. Please feel free. We probably have a couple of minutes and then we'll take a break before we start with the next talk.
Sounds good.
So in what application domains have you seen this being used, Silk and the framework?
So the biggest one we've done so far is this specification of C. So, it's a definition of the C programming language at the C11 standard. So it's a fair amount of work to build essentially a compiler for a language like that. And we've built extensions for, I think the biggest sort of application area is parallel programming. So this Silk is a language extension that comes out of that effort, but there's a number of different approaches to writing parallel programs. One of them we did recently was an extension based on this halide language, where you can write down your nested for loops for a particular computation over matrices or tensors. And after that specification, you write the program transformations you want to be performed on your code. Do you want to tile the computation of that matrix? You want to vectorize a particular inner loop. You want to parallelize an outer loop in a particular way. So there's various things like that we've sort of done, where I think parallel programming extensions are the biggest collection of extensions that we've worked on. So.
Nice. There is a question in chat. How can precedence order be unambiguously guaranteed across multiple extensions?
Yeah, that's a good one. So what we do is the host language grammar is set up in a way so that when I introduce a new operator in an extension, I have to be sort of explicit about the precedence level it slots into, and also the associativity. If it's a left associative, a right associative, or a non-associative operator. So this is a case where the host language grammar had to be set up in a way sort of anticipating these kinds of extensions. And so instead of having an expression, productions for addition, example being an expression is an expression plus another expression, we need different non-terminals for different kinds of expressions. So we have expressions that allow addition and all the operators of higher precedence. And then we have another non-terminal for expressions that contain multiplication and division and operators of higher precedence, but don't contain addition unless it's in parentheses. And so having this sort of hierarchy of non-terminals is a way we can explicitly encode precedence and associativity. And then this gives you the right place to kind of slot in your new operator. All right. And so that's how we sort of resolve these things. You can't introduce your own new level of precedence, right? They're sort of already defined. You're either equal to, between, you're either equal to an existing host language operator, or you're between two host language operators. And so two extensions that want to both be sort of have I guess, a precedence between addition and multiplication, they're going to have equal precedence, right? And they need to then be handled so that they have equal precedence and they also have the same associativity. All right.
Right. Thank you, Eric, for an enlightening talk. And we'll take a 10-minute break and continue with the second talk at 9:30.
All right. Thanks very much, everyone.
Welcome back. We'll get going now. The second talk for today is by Mattia Fazzini. Mattia joined us a couple of years back. He works in software engineering. His research interests are in techniques to improve software quality, closer to the kind of work I am doing. And his work is in testing and maintenance techniques, especially suitable for mobile applications, and about addressing security of software. Mattia, take it away.
Thank you very much, Sanjay. And I hope you can hear me and see me fine. And yes. That's great. And what I invite everyone to do is, if you have questions, feel free to raise your hand in Zoom or post something on the chat. I'm usually able to monitor the chat as well, so feel free to post any question in there. And today I want to talk a little bit about research I've been doing during my PhD and extending here as an assistant professor at University of Minnesota. And so really I would like to focus on how to improve software quality both before and after release. And I would like to start from, okay, maybe there are too many applications going on right now. Let's see if Keynote is able to catch up with Zoom going on. Let's see. Oh, okay. This is not good. This was not expected. And let's see what we can do. Actually, I was just kidding. This is just an example of how software can fail. And this is actually many of the failures that I experienced in the last few months. And actually, one of them is actually when I was submitting one of my job applications and the error pop up in the web application. So when you have such type of error appear, what you can do is usually that you have that something like this appears and you click the report button somewhere here. And then what happens is that you have that you submit the report and you send this information to the developer. So it's really important, first of all, to avoid that we make we release software with bugs, but at the same time, we should enable people to report bugs, and we should enable developers to actually being able to report, to consider and handle these bugs even after the software being released. So help them maintain software. And my talk today is going to focus on these two aspects, and I would like to provide two examples on why this is important. Well, first of all, we want to release software that is functioning, and so we need to improve software quality or assure software quality before release. And unfortunately, this was not the case when the health.gov website was actually released. So as you can remember, in 2013, health.gov website was released. It was full of bugs, and actually this software was not functioning, which delayed the ability of people to actually registering for health insurance. And this debacle was like ended in a formal hearing for the former Secretary of Health and Human Services. And actually, this person in the formal hearing said that the software should have been tested better. So it's definitely fundamental and essential to test the software before actually we release software. At the same time, it's also important to account for bugs and improve software quality after we release the software. And I would like to share an example here with an application, mobile application called WhatsApp. And this mobile application is used for messaging. And what happened is actually that this app had a bug, and user kept reporting this bug, but actually the bug was not fixed by the developers of WhatsApp. And so as one quote from this user that was not happy is that I'm facing this issue since June 2018. I sent too many emails to WhatsApp. So we really need to have a way in which we are able to report this information effectively so that developers can account for the bugs, so for the bug report that are received and for the bugs that are experienced by users. And so this is the kind of research work I've done throughout my PhD, and I'm continuing doing right now at the University of Minnesota as an assistant professor. So I focused both on techniques to improve software quality before release and after release. Actually, I also looked at this problem according to two dimensions. One is that I'm looking both at the functional quality of software and some non-functional qualities, such as the security of software. And so, for example, here we have that by non-functional, yes, I mean security. I didn't look at other non-functional qualities such as performance, but those should be taken care of as well. But what I like to do today is to actually focus on 4 techniques, present them, and discuss the more recent work. So how these 4 techniques, so where they brought me today and what I'm currently working on with my research group. And all of these techniques focus, as Sanjay mentioned, in the domain of mobile applications. So what I would like to ask maybe is how many people here actually have, that are watching this presentation, have experience in mobile development, so that that guy kind of gives me a feel. So if you have such experience, please click the yes button in the Zoom, if you don't mind. And if you don't have any experience, please click no. And that's totally fine. I just want to be sure that I'm using a proper terminology so that I can make sure that we are all on the same page. So I will wait just a couple of seconds to see whether so to have a certain amount of answers. We have 40 participants. I generally happy if half of the participants answer. So we have that some people actually have some experience in mobile development, but kind of the majority of people that answer do not have. So when I will make sure to explain certain concepts when I will go through the details of the techniques I will present. So thank you very much for providing this answer. So what I will do, I would like to kind of give a brief motivation why mobile applications are important. I'm pretty sure almost everybody using connected to today's talk actually are using mobile applications in their daily life. And maybe somebody is even connected using their mobile phone and using the Zoom app in their mobile phone. So you can see that mobile applications are pervasive in our daily life. And actually there are more than 5 million mobile applications on the Google and iOS store. And this mobile application generates an economy, which is $1.3 trillion. And just to put this in perspective, the overall economy of the world is 80 trillion. So this is a considerable chunk of money that rotates around the development of mobile applications. And why there is such a huge economy? Well, because we have a large number of users using mobile applications. Just some recent data is that there are more than 4 billion users using mobile applications every day. And if you think about that, that's kind of more than half of the world population using mobile applications every day. And not only people use mobile applications, they use them extensively. So a recent study found out that on average, people in the United States use mobile application for 2 hours a day. That's on average. And if you do some math, that means that in 1 year, people use mobile applications for 1 month. So these definitely are something that are important in our life. And we want to make sure that the quality of the software we are using is high, and we need to ensure this both before and after release. And the way in which this is possible, so the reason why we have these many mobile applications is that we have more than 10 million mobile developers. And so we need to make sure that they have the techniques and tools to properly test and maintain the software. So the first part of the talk will be focusing on testing. And the second part of the talk will be focusing on maintenance. And I will start from the testing. And specifically, we start with a technique which helps developer generating test for mobile application. And this technique is called Barista. So as I mentioned, mobile applications can have bugs, and one way to identify or to reveal these bugs is actually that we have that mobile application. So yeah, that there are different techniques for testing. But the majority of people, according to a survey, is that they still prefer to test the mobile application manually. So it's not that they prefer, but there are not enough tools, or there is not the right techniques to actually, for them in their development life cycle, to actually use testing tools, automated testing tools. And this was a study done in 2017. And so the 58% of the developer actually performed this task manually. So what we did is to create a technique called Barista, which helps developer in the task of manual testing. And as they do manual testing, it also creates executable test cases, which developers can take and execute on different devices. So the Barista technique that we defined is divided in 3 parts. The first part records actions as the user as the developer is interacting with the application, as the tester is interacting with the application. And the neat part about this technique that not only you can define interactions, so you express interaction with the application, but you can also define oracles for the test. So the test that this technique will generate has both interactions and oracles are in the form of assertions. And the second phase, it actually encodes this information into an espresso test case, and that's why we named the technique Barista. And then finally, the last part of the technique actually execute these test cases not only on the device in which it was recorded, but also on other devices. And what I would like to do now is to actually give you kind of see the third part of the technique. I have a short video here on where we were running this experiment. So this is one of the test cases that Barista generated, and you can see how this test case can actually execute on different devices which have different format and also on emulators and so on. So I want to talk a little bit on how we evaluated the technique. So first of all, we checked whether actually developers can record, so testers can record test cases that they want, and how actually this compares to existing tools. And we consider test recorder and espresso test recorder. So we found out that developers could record 100% of the test cases they wanted to record, while with the other tools, they could not do as many. And the most important thing and the most striking difference is that Barista has a better support for the definition of assertions. Then we also measure how long does it take for tester to actually record test using the 3 different tools. And we found out that Barista was actually faster. So developers were faster in recording test cases using Barista with respect to both Espresso test recorder and test droid recorder. And finally, I mentioned that our technique is also able to generate test cases that can run on different devices. And we consider 7 devices, and we found out and we measure how many of these test cases actually execute according to, so are able to execute also on a different device. So I remember we had something around, so the testers created 225 test cases for 15 applications. So we ran all of these test cases on 7 devices, and we measured the number of test cases that were successful, so were passing. So there was no failure generated on a specific device. And then we manually checked for the failures. So you can see here how Barista outperforms of the tools. But still, if you look at the number, we don't have 100% here, right? And so it's Barista is can almost handle all possible test cases, but at the same time, there is a 0.8% which is missing. And this is due to the fact that some of these devices have a customized operating system, and this affects the behavior or the information that is being displayed on the GUI of the mobile application. Same mobile application running on 2 different phones, behaving differently. And this is actually what I would like to talk in the next part of the talk. So in these 2 first topics, I'm not going over the details on how we did things. I'm just presenting general techniques. I will focus more on the details of the 2 maintenance techniques. But if you have questions about how this is happening, feel free to stop me. I'm happy to provide more details on these 2 first techniques. So the thing that I want to talk next is about mobile applications in the context of Android. So the Android ecosystem is characterized by heavy fragmentation, and this fragmentation spans over 3 dimensions. One, you might have that the device has different hardware, and so a mobile application behaves differently because of different hardware. You might have the device as a different customization of the Android operating system. So it's not uncommon for vendors to get a competitive advantage over other vendors to actually customize the Android operating system, as it is open source. And then your application might not behave as expected on this device. And finally, you have a particular type of hardware, which is actually the screen. The screen might be different in size, might have different pixel density. And so even that might lead to a different behavior of the mobile application. And just to give you an idea of how different these devices can be, I want to show you a small video on a device that was released in early 2019. And this was at a conference, and this device, as you can see, it's very particular, but still people and testers, so developers, need to make sure that the apps they create actually behave as expected. also on these devices. So what we have here is that the current situation, is that developers and companies struggle quite a bit to actually support testing on or making sure that the software doesn't have, making sure that the testing activity is performed on these different number of devices. So what happens is that you have that Salesforce dropped support for certain Android devices and only kept support for Samsung and Nexus. So as you can imagine, customers were not very happy about this, but companies really struggle to identify a testing technique or a testing procedure to make sure that the app behaves as expected on different devices. And then also in 2018, you have the WhatsApp drop support on specific versions of the operating system. And so this is a very significant problem. And what we did is to look into this problem, and we propose a technique to actually help developers identify these inconsistencies. So I want to give you a motivating example to make this idea a little bit more concrete. So you have on the left of this slide, you have LG G3 displaying a certain mobile application. This is called Daily Dosen app, and this is for daily intake of nutrients. And something you can see the same application running on an LG Optimus L70. So based on these slides, can you see whether this mobile application has some issues or some potential issues? And maybe you can post in the chat, you can raise your hand and you can tell me what type of, so somebody is saying, yes, this application has some issues. Maybe you can post in the chat or raise your hand and say, what's the issue that you find? Okay, I see Survanan. Sorry if I misspelled the name. Why don't you unmute yourself? And
yeah, I see like on LG Optimum L70 has a overlapping of calendar icon over the selections of other vegetables.
Yeah, exactly. That's one of the issues that this application indeed have. As you can see here, this checkbox is overlapping with the calendar icon. And so this is a non-desirable property of this application, because you want to be sure that everyone is able to properly check that checkbox if needed. And then there is another comment from the chat. There is Alex, and that is mentioning that the checkbox next to crucifer vegetables is not present, I guess, on the LG Optimus device. And you can see here that actually what you have is that on this device, you have a checkbox you can click. And here this checkbox is actually not clickable because it's not even present on the screen. So what we wanted to do is to focus on this. And there is also another comment on the chat that we cannot see the whole list. The thing that I couldn't display in this slide is that this list is scrollable. So yes, it's not present there, but at the same time, you can scroll and see all the elements. So what we actually, that's one of the challenges that we had to face in this defining this technique, is that there are some differences which are indeed the differences, so inconsistency. We call these cross-platform inconsistencies. But there are some others that you need to actually explore the application to realize that there are actually not inconsistencies. And so what, as I mentioned, we have two types of inconsistencies. And this is the technique that we designed to actually identify these inconsistencies. So the technique works in 4 different phases. And in the first one, we explore the application while collecting some information about the application. And specifically, we collect a GUI model of the application running on a reference device. And what I mean by reference device is that this device is a device that the developer or the tester is confident that the application is working as expected. Has already run the test cases associated, the test suite associated with the application on this device. The developer is confident that the application is behaving as expected. So during this exploration, we collect information about the GUI, and then also information about the inputs that we generated to exercise the mobile application. So then what we are going to do, so what the technique does is to actually encode this information into test cases and a model. And then in the third phase, we actually re-execute the test case, but not on the app running on the reference device, but actually running on a test platform, so other devices. And what we do is to actually collect a UI model for each of these test devices. And then in the core of the technique, we compare the model of the application when running on the reference device with the model of the application running on the test devices. And the idea here is that we want to find inconsistencies. And what I will do next is to actually describe these, the details of this comparison. I will not actually mention about other things, how other parts work, but feel free to post in the chat or if you want to know more about that. So what we have here in this fourth phase, the core of the technique, is that you have a reference UI model and a test UI model. And this model is composed by two components. One is a GUI hierarchy. So I remember that some people were not familiar with the mobile application. Maybe they were familiar with web development. And so the way in which the GUI is organized in mobile application is fairly similar to web application. So you have a tree, and this tree encodes the information about the GUI. And so what we do is to actually capture these tree. For each screen that we explore, we actually collect the tree and also a screenshot of the screen. And here, what we do is to actually even filter out some of the screens which are repeated throughout the exploration. And the way in which we do the exploration is doing random exploration. We have the same information for the window, so for the application running on a test device or on all of the test devices. And what we have here is that first, we compare the two trees. And the objective of this comparison is to actually find structural differences. And if you remember about the motivating example, the checkbox missing of the application. And the way in which we do this is to actually by doing, we have an heuristic to match nodes in the two different trees. And so we also have heuristics. So once we identify whether a node is missing or not, so we have a node that is not matched, then in this case, we further check whether this node is actually an inconsistency. If that's the case, we report this inconsistency to the developer. Otherwise, if we can find out that this element is part of a list that you can scroll, then we will not report as an inconsistency. So we have some heuristic also to remove some of the false positives. So this is about the first part of the comparison. So the first part focuses on finding inconsistencies at the structural level. Then we also consider the screenshots, and when we did this work, actually deep learning was just taking off. So we didn't use a deep learning technique to identify these inconsistencies. What we do is to, for each leaf in the tree, we take the part of the screenshot representing the leaf and comparing this part of the screenshot with the matching node. And we use a decision tree classifier with some features which range from the color, the scale of the picture, and so on. And then if the decision tree classifier that we trained on a sample of a screenshot says that we have an inconsistency, then we report this inconsistency to the developer. So what I would like to do is to actually present how we evaluated this technique. So how many, so the first we evaluated the effectiveness, and by this I mean how many consistencies we identified and how many false positives we had. And the type of false positives might be given by the decision tree classifier. So we consider 5 benchmarks. Those are open source apps available on GitHub. The reference platform that we used was a LGG3 running Android version 22. So we did this study in 2000. So we did this work in 2017. So the version of Android is a bit outdated. That's the reason. And then we consider 147 devices. And the way in which we were able to do this, of course, I didn't have all of these labs in my lab. That would be kind of a dream, having this many devices in my research labs, but actually that's not really feasible. So what we do is to use the AWS device farm. They kindly gave us some free credit to actually run these experiments. And what we did is we had a variety of devices in terms of resolution, versions, and also vendors. And what we could find is that by running our technique, which is called diffdroid, on these different devices, we were able to identify 96 inconsistencies. So those were manually verified by us by checking screenshots and trying to reproduce the inconsistency. And at the same time, we saw that the false positive rates was 14%. So 14% there were false positives. And of course, we believe that this type of result is encouraging, and this technique could be used by developers. Another thing I would like to mention is that, of course, this is all good if the cost of the technique is manageable. And we measure the cost of the technique. So how long does it take to run these experiments for one app on these many devices? And actually we found out that in all of these cases, you could run all the test cases overnight. So you can think of this before a certain release, you run all these approach, and then you have a report in the morning that developers can actually look into. So that's how this second testing technique works. So the first one focusing on generating test cases, actually providing a way to automate the testing process. And the second one actually works, and it's about a specific problem of mobile applications that is this fragmentation of the ecosystem. And what I would like to do now is to actually switch page and now talk about maintenance. So how to take into account about bugs after release. And I will start from a technique which focuses on bug reports. So even in this case, how many of, so I know that most of the people that are connected here today are part of the MSSE program, has some working experience. How many times it happened that you received a bug report, but you couldn't reproduce? So click yes if you experienced that, and no if actually you never experienced that. As usual, I'm waiting a few seconds and actually drinking something. So, as I'm waiting. And if you don't know where the yes button is actually, you can, it's in the participant window. So you click participants, and then at the bottom, you should have the yes and no buttons. And I see that, for example, Coring is saying that it happens often. And I can relate to that. To the extent that we did this work on purpose to kind of help this process of reproducing bugs. And I will just, in a second, describe how we did this. So, so far I have 18 answers, 19 now in the chat, and all 19 actually experienced this problem. Yeah, it's the usual saying, well, it works on my machine. Yeah, it's kind of very popular thing as we develop software. So, and somebody, Andrew, actually is trying to hunt down a bug for tomorrow. So that's something that people relates to. And I want to talk about this, and specifically in the context of mobile applications. So thank you again for answering about this in the chat. And what I would like to say is that we saw that we can have, we develop software and we have bugs in the software, but also when we do testing, it might be that we have some latent bugs still in the software. And of course, we cannot practically do exhaustive testing. And so in the majority of the cases, and so it might be that our software is shipped to the field with some latent bugs. And so what happens is that these bugs, if are exercised by users, they appear in the form of failures. And user, when they want to report the bug, they can do so and send a bug report to developers. And the task that developers need to do to actually correct this bug is called corrective maintenance. And so developers fix the bug inside the mobile application. So the very important thing about mobile application is that users do not tolerate failures very much. So users will try a failing app at most twice. So 80% of the users, so great majority of the user, will try a failing application at most twice. What this means is that if your application failed twice, then your user will not, so you don't have users anymore. So this is a very important problem that you're able to fix these bugs very quickly. And our work focuses on this topic, as I mentioned. But what I would like to do is to actually first present a little bit the type of information you might find inside the bug report. And you have expected behavior, observed behavior, steps to reproduce. Sometimes you have a stack trace, sometimes you have a screenshot. This is specific to GUI software and in particular mobile application. But the thing that really is something desirable for developers, and you might relate to that, are steps to reproduce. And so the only thing, so the thing I would like to talk about a little bit is about this specific topic, and our work focuses on the steps to reproduce. And the reason why it focuses on this topic is that we actually want to help developers in reproducing the bugs. And what you might find, so this is an example. So this is an example of a real bug report for the WordPress application. The WordPress is a blogging application that you can use to post, to create blogs and make posts. And so in this application, in this specific bug report, the steps to reproduce were the following. So the first step was actually start a new post. And the way in which you can do this is to actually by clicking the icon in the bottom right corner. But you can see here that there is kind of a semantic gap between the language used in the bug report and the actual GUI action that should be performed on the GUI. So for us, it makes us, as humans, it makes a lot of sense to know, so to understand what is a start a new post. But a machine, it's actually reason in terms of executable actions. So in this case, it will be a click. So here there is a gap kind of between the information provided by the user and the action that actually is performed on the GUI. The second step in this bug report is actually typing something on the screen. And so this is kind of fairly straightforward. There is a text box. We should be typing something. The thing that it might not be obvious is that actually you have two text boxes here. So the user didn't really specify which text box we should use. And so the developer needs to try both boxes in order to be able to replicate this bug. Finally, we have the tap publish button, and this is a specific GUI action, so the developer and machines can perform this task fairly easily. And finally, the user said that the application crashed, and so this is a kind of a screenshot of what happens when the developer might successfully replicate the bug report. So what usually then developers do is it's good practice to actually, once somebody reports a bug, you reproduce the bug and actually encode this information in a test case. And this is the test case corresponding to the specific bug report. And the idea why developer, it's a good idea to do this is because then you can prevent the same bug from appearing in the future. So you can add this test case to your regression test suite, and you can prevent the bug appearing again. So the idea is that developers are really interested in having this information, and because it can help a lot with the debugging of the application. So what this means is that, for example, you can think of doing something like fault localization based on the information provided by a test case. But actually, if you don't have these test cases, all these type of automated techniques that you might want to use as you're debugging your mobile application cannot actually happen. So what actually our work aims to do is to automatically translate a bug report written in natural language into a test case. So there is no developer in the middle. Our technique that we define takes these bug reports, analyzes the content, and does other things with the mobile application, and then generates a test case automatically, which reproduces the problem described in the bug report. So the kind of challenges in making this transition automatically is that reporters generally are kind of familiar with the application. So they assume certain action don't need to be reported. So there are a lot of missing steps. And so an automated technique needs to take into account about that. There could be ambiguous information. For example, type something, in which type of text box should I type this information? And finally, there could be also a semantic gap. So an automated technique, because is an algorithm, really needs to bridge this gap that you might have in the language contained in the bug report and the language and the actually the type of executable actions you can make on the device. And so what we did is to actually create this technique, which is called Yakusu. And here it's not the name of the Japanese mafia. This actually is the Japanese word for translating. For the verb to translate. So the idea is here that we wanted to give a name that is translating a bug report into a test case. And the way in which this approach works is actually in 3 ways. So first, it gathers information about what's inside the mobile application. And then it processes the bug report using natural language processing and binds this information to aspects inside the mobile application. And these aspects we call the ontology of the application. And this second step actually produces a set of abstract steps. And the reason why I call them abstract steps is because they are not in executable format yet. And the part of the technique which takes care of that is actually the UI, so the third phase, which we call UI action search, which actually maps this abstract step into executable action. And when the technique is able to do that, encodes this information in a test case. Now, I don't want to say much, so I will talk first about gathering information about the app content. And so for the people that are not familiar with mobile applications, in particular with Android applications, you have that these applications are kind of built in 2 different ways, using 2 different type of files. One is some configuration files, which configure the GUI, so how the GUI looks like. And the other one is the code, which defines the business logic of the application. And in the code, you can also define GUI elements. So it's important to consider both information when you want to understand the content of the mobile application. So the way in which we analyze the application is by using static analysis. So we analyze both XML files and the code. And we extract information about the GUI elements contained in the application. And we encode this information in the form of tuples. And these tuples are part of the ontology that you can see right there at the top. And so the 3 information that we collect for each GUI element is a label. So the label displayed to the user. The icon name. So if you have an icon, you might not have some type of info. So you might not have an alternative text associated with this icon. And so you might just have a name associated with this icon. And then this name is not displayed to the user, but it's usually manually defined by the developer. And so this is kind of the intuition on why we are extracting this information, because it's a descriptive way of something that is on the GUI. And the user might use a similar terminology to describe a certain GUI element. And similar reasoning applied to identifiers. Identifiers cannot be seen by users, but they are defined manually by generally they are defined manually by developers. And so they have some semantic meaning associated with the GUI element that they describe. And just to give you an idea, for the element representing the starting a new post, the alternative text associated with this GUI element is new post. And then you have that the create, so the name of the action is create Y, and the identifier is FAB button. And so what we have here is that this tuple is then put inside the ontology, and this information is provided to the next phase of the technique. So next, what I mentioned at the beginning, what we do is to actually analyze the bug report and using natural language processing and leveraging the information that we have in the ontology. So the idea is that we want to use a bug report. So we get the bug report, use the ontology to extract abstract steps. And these abstract steps are composed by 3 elements. One is the type of action. The second one is the target, so the GUI element associated with the action. And finally, we might also have some properties. For example, if the user side type 1, 2, 3 in this text box, we might have some properties that we want to extract from this text of the bug report. And the way in which we analyze sentences, so this goes into a different area of computer science, is not software engineering more, but we are seeing more of this in software engineering, is natural language processing, and specifically the technique that we use to understand the content of this bug report is called dependency tree parsing. And so we have for each sentence a dependency tree representation. And here you can see the tree representation, which is for the sentences that are in the bug report I provided as example. And what we have here is that the technique actually operates into, there are 2 cases. One is that once we parse this graph, we have some rules and patterns in which we identify the root word, and if this root word represent a GUI action that we are aware of, then, so in this case is tap is like click, press. So if we have this type of keywords in a certain position of the tree, then we are able immediately to identify that this abstract step, the action type should be a click. And based on the relation expressed in the graph, we are able to exercise by the action. In this case is the publish button. And then in the similar way, we can extract attributes associated with the action. In this case, there are none because this action doesn't take any attributes. The second case is a little bit more complex, but is able to give us a way to handle sentences in which they have a semantic gap, so they don't clearly state what GUI action should be performed on the GUI of the application. And start a new post is an example of that. So if that's the case, when we analyze the tree, we actually extract this information and we compare this information to, so we consider the sentence as a whole, and we compare this sentence with elements, so with the properties that we have in the ontology. And just as a reminder, this ontology is that we have that this ontology contains information about GUI elements in the application. So we want to see if the sentence relates to the GUI elements in the application. And we do this using word embeddings, and specifically word embeddings built with word2vector. And pretty much give us two vectors. We compute cosine similarity, and we find if the two, so the sentence is similar to the textual description. So the description that we have about an element, then we say potentially we should perform an action on the element represented by the sentence. And so we are not aware in the abstract step of what action we should be making on this element, but we can say that this element should be exercised somehow, possibly. And then we don't have information about the properties because we are not able to recognize what type of action is that. So finally, we want to create executable test cases based on this information. And the way in which we do this is to map abstract steps into GUI actions. GUI actions follow a similar structure. They have a GUI action, they have a GUI element, and they have some of properties. And the way in which we do this is by using a guided search or guided exploration of the app on a device. So we install the app on the device and explore the app based on the abstract steps we would like to map into GUI actions. And so the general idea is that this exploration is guided by the elements that we have in the GUI action. And once we try to map an element into the GUI of the application, we always do word2vector. And the reason here is that we have a textual description in the abstract steps, but this description might not match what we have in the GUI. By using this kind of semantic similarity comparison through word embeddings, we are actually able to bridge this gap and associate, for example, publish button just with the word publish. And in this case, we have three cases. The simple case is when there is only one button which matches our abstract steps. So we perform the action on this button and move to the next state of the application. At the same time, we might have that we actually have multiple choices for this button. You might think publish, quick button, publish, safe button. There might be two buttons in the GUI. So in this case, the technique is not really, so it's able to prioritize these buttons, but you don't have a clear signal on which button you should be actually clicking. So what we do is to actually conceptually fork the execution, and then we perform the GUI action on the most promising element. And in that case, we then continue the exploration. But if we find out that at the end of the exploration, we didn't reproduce the bug, then we go back. So we go back to the state when we forked the execution and continue from the other state. Finally, what we do is to actually look at so it might be that the user didn't specify a specific step in the bug report. And so what we do is to actually perform random exploration to account for that. And we define a limit of actions that we can perform before actually giving up the exploration in that specific state. And finally, when we have all the actions that are performed, we can map them into a test case, and then we can tell whether we can reproduce the bug. And here in this work, we simply focused on bug reports leading to a crash. So it's very easy for us that the bug was reported. And indeed, Sanjay, as I was mentioning this, wrote in the chat, how do they detect that a bug is being reproduced? So that was the question from Sanjay. And the reason why we can do that is by actually looking. So in this work, we are only looking at crashes. And I think a very interesting option for future work is to look at non-crashing bugs. And so try to see if we can encode assertions into, so sentences into assertions so that we are able to actually handle non-crashing bugs. So the way in which we evaluated this technique is by looking at the effectiveness of the technique. We consider 100 random bug reports from GitHub. And actually, we were able to manually reproduce only 62 of them. And the reason is that you might have outdated dependencies. The server side might have changed. So not all of them we were able to reproduce manually. So we didn't even consider them the other one that we were not able to manually reproduce, as the technique didn't have chance to actually reproduce them. And of these 62, actually, our technique was able to reproduce 60% of them. And we didn't impose any structure on the bug reports that we considered. We just picked the first 100 random one. And I want to give you some details of the technique. So what happened as we were reproducing these bug reports automatically. So we had the 9 bug reports at least one missing action. So this action was missing from the bug report, and the technique was able to reproduce them. 7 bug reports with at least one step not having a explicit action. And this means that there might be start a new post. So 7 of these bug reports has such type of language in the bug report. Then we have 31 of the 37 bug reports. We were able to reproduce by only doing one exploration. So we forked the execution, but we were efficient in picking the most promising action using semantic comparison. And finally, we have 6 bug reports reproduced more than one execution. So this gives an idea that even if you don't pick the right element, you must be able to explore different executions. And finally, because we are using some random testing and some bug reports as missing actions, we perform random exploration. And in 4 cases, we had more actions than needed in the bug report. So the test case we reproduced was not the minimal one, but we were still able to reproduce the bug. So how long did it take to actually reproduce these bugs? So the bug report that took the longest took 30 minutes. So you can see how you can actually adopt this in daily development. Bug reports are submitting. You have this background job which try to reproduce them. And then when this bug report is reproduced, then the developer is notified and can immediately focus on debugging and localizing the fault. So this concludes the first of the 2 maintenance techniques. Sanji, correct me if I'm wrong. I'm assuming I have till 11. And
yes.
Okay, great. So we have time to look into the details of this second technique. This second technique, it's related always on maintenance. And so what I would like to focus your attention on is that these mobile applications actually run on a specific platform. And it actually, there is a tight coupling between the application and the platform. And for people that might be not that familiar with mobile development, this coupling is created by the fact that the platform provides an extensive API, and these applications rely heavily on the API. So you have that when the app platform changes, then you might have issues within your application, because a change of the platform, so a change of the version of the API running on the device might create new bugs inside your application that you're not aware of. So it's always good practice to, if you can, update to the most recent version of the API. And of course, this task is very time consuming. And in this work that I'm presenting an automated technique to account for this type of issues that might arise. So as I mentioned, you can have bugs. And the thing that is particular about mobile application is that this platform changes very frequently. And these are simply the major version released for Android in the last 10 years. So you can see how more often you need to So almost every year, if not more often, and this is just for major releases, you can also have minor releases, and you have to do that. You need to perform this task of actually upgrading your application. So you don't have to, but it's a better practice to, because the changes might be deprecated, and that so an API might be deprecated. In that case, there is no guarantee that your app will continue working in the future. So when a new platform is released, developers is thinking, how should I make these changes? So there is this API. This API changed. The documentation tells me that the API has changed, but the documentation doesn't really tell me how I should make this changing. And the other problem that you have is that once you make these changes, as I mentioned, the fragmentation of the Android ecosystem also have that you have different versions. So your app might be running on different versions at the same time. So one user might have a version 29 of Android, another user might have version 22. You want to make sure that your app operates suitably on these two devices. And so developers need to take into account also of these things. So I upgrade my app, but still I need to upgrade in a certain way that also runs on a different device, older device. But there is a silver lining here. In fact, if you think about all developers work, so implement their apps using the same API. So the API provided by the system is the same. So if one developer make a change, then we can actually reuse this information to automatically upgrading the app of the other developers. And this is what actually our technique does. And what we have here is that I would like to present this technique using an example. So this example is based on API usage. And by API usage, I mean the application is using some calls of the API. And this is the get all network info API call or API usage. And this method was deprecated in API level 23. So in the version before 23, you have that the old API usage is a get all network info. And in the new version, you have that this call has been replaced by two calls. One is get all networks, and the other one is get network info. And these two should be suitably combined in order to get the same result. So what I would like to highlight here is that not only you have differences in the names and the number of methods, you also have differences in the parameters and return values used by these API usages. And because I'm using it extensively in the next few slides, I'm doing some color coding here. And for the old API usage, I will use the color red. And for the new API usage, I will use the color. So the codes involved in the new API usage, I will use the color green. So here it's an example of an update that a developer performed. I don't want you to focus on the code. It's a bit busy. I will go through this highlighting the important things about this code. And what I want you to realize is that on the left of this slide, you have the code before the developer performed the upgrade. And on the right, you have the code after the developer performed the upgrade. So what I would like to do is to actually tell you what this function is doing. And this function is checking whether the device is connected to the network. The way in which this is done is by calling getting network information from the system, iterating over the different type of connections and checking whether a certain type of connectivity is present. If that's the case, this function returns true. Otherwise, displays some text and return false. In the new version, we have some changes. And first of all, I would like you to see, to point your attention to the fact that here we have a condition, and this condition checks on which version the app is executing. So on which version of the operating system the app is actually executing. And what we have here is that if the app is executing on the new version of the API, then it's using the new API usage and doing the same operation. So you have get all network info, returns networks that iterates over the network information. And you can see how this is actually syntactically different from what was done before. And while if the code is running on the old version, you have that the application is using the old API user as it was done before. And something I would like to add is that you have this combination, and so an automated technique that would port this information to a different application needs to be able to handle these two different cases. But there are also additional things that have changed. And these things are not related at all to the API usage itself. So here, for example, in the new version, as the developer was making these changes, actually added some logging information into the code of the application. And this is something we don't really want to port in a different application because this information might not be necessary. So we need to have a way to actually recognize this additional code that is not necessary. And then finally, there are also changes to information being displayed on the screen. And even this type of changes are not really relevant to what we are doing. So to actually make these changes, we define a technique which is called app-evolve. And app-evolve operates in 4 phases. And I will talk about each phase in detail now. So the first phase is API usage analysis. So what we do here, we get the application that we would like to update. And we also take a specification of the changes. And this specification is is pretty much a mapping. This method should be mapped to these 2 other methods. And what we do is to actually check whether the old API usage can actually execute on the new version. As I showed in the example before, developer might make some checks that only execute this API usage only on a certain version. So we don't want to upgrade that because actually the upgrade is not needed in that case. So what we do is to use static analysis, and we actually extract this information. So we only identify whether the API usage that we want to upgrade is present and can actually execute on the new version of the system. If that's the case, we save this information and we want to upgrade this API usage. So migrate this API usage. The second thing is that we need to identify examples. And of course, we could do this manually, but it's much more efficient if we automate this. And the way in which we automate this is by using a code hosting infrastructure. In our specific case, we use the GitHub. And first of all, you can imagine how many repositories there are on GitHub. So actually, to give you not the exact number, but a kind of estimate, there were more than 50 million public repositories on GitHub. I think this number is from last year. And what you want to do is that when you have such a big number of repositories, it's not really practical to do a search which is based on static analysis of the application. So you want to have a quick way to actually quickly prune out some of the results which are likely not to give you any good example on how to upgrade your application. And the way in which we do this is by using a keyword-based search. We extract some keywords from the API usage and make a search on the repositories. This gives us some possible results. So here I would like you to pay attention on the fact that in this case, this repository might not contain the real API usage that we are interested in. We need to make further checks. But at least we have some in repositories, some prune out number of repositories that we might want to check. And here, what I would like to do is to tell also that not only we have this repository, but we also have their version control history. And we are actually going to use the version control history. So what we do is to compare a certain file that actually possibly contains the API usage, because we did a keyword-based search, and compare this version with the previous version. Do we have an update there that we can use as an example? And the way in which we do this is by comparing the diff and finding whether the new version added a check, and inside one branch of the check, we have the new API usage, and in the other branch of the check, we have the old API usage. So this is the information that we use to actually determine if a certain result given by the keyword-based search is actually a real example on how to perform the migration. And so if that's the case, we consider this as an update example. And of course, by doing this process, we might have multiple examples on how to do this. And the next part of the technique actually leverages this information or this idea that we might have multiple examples on how to actually perform the migration in our target app. And so what we do is to actually want to extract only the relevant information about the API usage from the code. What we do is to analyze the abstract syntax tree, and actually we compute an update patch. So how can we translate one abstract syntax tree into the other? And the way in which we do this is by extracting some tree operations, and that make us transform one tree into the other. And the algorithm that we use is from related work. It's called change distiller. And this algorithm, it's actually able to provide you this script, which tells you how you should move or add node around, or even delete nodes. So this is an example of script that we get from the example I showed before. You have an insert operation, an update operation, and so on. And what I would like you to focus your attention is that there are some unrelated edits. For example, I told you that we make a change on the information that is displayed on the screen, but we really, this change is not related to the upgrade of the API. So the way in which we remove this type of change is by computing dependencies in the code and removing things that are the changes that are not related through a dependency based on the information of the API usage. So if this change is not related to the API usage through a chain of dependencies, then those are code dependencies. Then we don't consider that specific edit operation. Then we also have additional information, such as we have some edits, and I showed in the example that we have log information added to the specific example. And the thing here that is different from before is that actually this log operation is related to the code, so to the API usage, because it has a dependency. So we cannot really safely prune out this information, but we don't really want this information. So we need to take a further step to remove these unneeded edits. So the way in which we do this is to actually compare different examples. So compare the scripts obtained by different examples. So here, what you're seeing is that this is the first example that I showed, and this is another example. Both are edit scripts. So what we like to do is to actually, can we compare these two to actually only get the relevant information about how we should change the API usage? And the way in which we do this comparison is by using by solving a multiple longest common subsequence problem. So we have different sequences, and we want to find the largest sequence for each of the examples and compute something that is called core proximity value. So basically, this is a number. How close is the sequence of a certain example based on the sequence shared across all of the examples? And here we might have 5, 6, 10, 11, 20 examples. So we want to see what's shared across all of the examples and how close each example is to this core that is shared across all the examples. And once we have this information, we can actually rank these examples by the proximity value, and then try to apply the example which is more closely related to the core across all of the examples. Before actually doing this update in practice, we need to identify one last information, which is how can we actually place these changes performed? Where should we place these edits in the code that we are trying to update? And so we have some variables used by the script, which can actually help us. You have some variables which we call context variables. And these variables are variables which are free in the sense they are used in the script, but they are not defined in the script. So this is kind of our connection points with the code that we want to change. And as I mentioned, we call these context variables. So this information, so the script, the core proximity value, and the context variables give us an update patch. This patch is actually able to tell us how we can change a certain application. And as I mentioned, we can rank them based on the proximity value. So how closely related they are to the core shared across all the examples. Finally, we can perform the changes. So this is the code of our application that we want to actually change. And as you can see, it's using the old API usage. And we will start trying to use each example, so each patch one by one, and see which one works. And the way in which we determine whether this works is that we check at every point at every statement in the code whether this patch can be applied or not. And this is determined by using the abstract syntax tree. So we are actually solving, we are applying the patch on the abstract syntax tree. And once we apply this patch, we are actually able to generate a new abstract syntax tree. And this new abstract syntax tree gives us the code of the updated application. And something I would like to mention here is that you might have that a patch is not applicable at a certain point because either the operation of the edit script cannot be performed. So you might need to remove a node, but this node is not there. So this patch doesn't work. Or that the context variables are not available at a certain point of the code because they are not defined yet. So in this case, we will not be able to apply that patch. So we need to look at a different statement, a different position in our method. And this is how we upgrade this information. We did this, so we are able to generate code that compiles, but actually we are not able to tell whether the change we made preserved the semantics of the program. And the way in which we do this is to actually perform differential testing. So we execute the app on the old platform with the old code, and we collect execution information. Then we execute the updated app on both the old version and the new version, and collect execution information, and compare this information with the old information, and make sure that actually nothing has changed. Of course, we are doing testing here, so we are not checking all possible behaviors of the application, but it is a way to provide confidence to the developer that actually this operation works. Also in this case, we checked effectiveness and efficiency. And I would like to talk about the benchmarks we used. Those are open source apps on GitHub. And we consider 20 API usages, and these are the API usages that are present in these 15 apps. So we consider all the API usages that they were using. And also, I didn't mention, but these apps are from 3 different versions of the operating system. So we wanted to see whether we can generalize our work also to different versions of the system. So the way in which we evaluated our technique is to run the technique on the benchmarks, measure successful update and validation rate, and measure the execution time. So in 85% of the API usages we consider, we were able to successfully update the app. So we created the right version, so the new version was correctly implemented. Then if we consider all occurrences of these API usages, then our success rate raises to 90%. The thing that it was not as, so let's say we could only validate, so we couldn't validate all of the updates we perform automatically. We could validate them manually, but not automatically, is that for limitation of exploration, that you might not be exercising a certain change automatically. And so we were not able to say automatically whether that update was correct or not, but we manually validated and it was. So 68% of the cases, we are actually able to automatically tell whether that was correct or not. And when I say correct, this is within the context of testing. And some details is that for all but one case, we could find examples on GitHub. So for one API usage, we couldn't find any examples. And this doesn't mean GitHub doesn't have this update. It means that our search, keyword-based search, might filter out some results which are actually useful. And here there is a trade-off between efficiency of the search and thoroughness of the search. Then in 14 out of 19 cases, the number of relevant edits is lower than the number of AST edits. So this gives you an idea that when you compute the script, then you want to reduce the script because there are unrelated changes. So this appeared in 14 out of 19 cases. And in 11 out of 19 cases, the changes across different examples are different because their core proximity value differ. And so in this way, we really need to, so it's not possible you just pick one example and you use that one. You really need to compare different examples to know the best way to perform this update. So, so in terms of effectiveness, we consider this technique to be fairly effective and we are happy with the results. In terms of updates, most of the steps took just a few seconds to run. The longest step was the search, for example, which took roughly 10 hours. But we don't think this is a problem, as this step needs to perform only once you're trying to upgrade. And these results can be shared across developers. We didn't do any effort in parallelization. So this technique of this step of searching, for example, we don't see as a problem. So I would like to make a recap. So I presented some techniques for testing and maintenance. And I also, specifically, I presented techniques for generating test cases, doing cross-platform testing, doing some bug report analysis, and making changes to the environment. So in terms of what we are working now and what we will be working in the future in my research group, we would like to automatically create test mocks for this application. So in our study, we didn't see cases in which application were using network connectivity, which was making the application behave not deterministically, but that could be the case. So you might want to automatically create mocks. And also, we want to look at our hardware inconsistencies. So we look at GUI inconsistencies, might be hardware inconsistencies that are not appearing in the GUI. We want to see whether we can identify inconsistency between different software domains. We have a mobile version of the app, we have a web version of the app, and we want to actually compare these two things. And then we want to be able to automatically generate bug reports from executions or crashing execution, if that's possible, or even help developers write better bug reports. And finally, about supporting changes to the environment, we can think of how to combine update and repair to actually make this process more efficient, or how to automatically generate the specification from the documentation. And this specification is the mapping, how to, instead of manually creating this mapping, how do we actually automatically extract from the documentation of the software. So I have a few more slides which kind of present future work. I know I've talked a lot, so I'm taking a break right now. I know we also have just a few minutes, but you might ask, so if you want to ask any questions now, we can focus on the questions, or I can go forward and present two topics very shortly that present what we are working right now, and we have some results about this. Right, I don't see any questions, no hands raised. I have one, Eric. Oh, go ahead, please.
This is a question about something you talked about earlier, the Yakusu work.
Yeah.
So I was curious if this whole idea, right? You can translate a bug report into, or sorry, a report from users into a test case. Is that correct?
Yes, that's correct.
And so that seems to me there's a big semantic gap here between what the bug report is that somebody wrote in natural language and the code over which you need to then generate actions that executes per certain parts of that code. Mm-hmm. So it sounds like a great thing, right? If I could get bug reports to just be processed automatically. Does this motivate you? Would this motivate people to change how they write their code so they can write their code in a way that improves the performance of your system, right? That if I know that there's this technique that will generate test cases from bug reports, can I write my code? Can I annotate my code in certain ways that kind of raises the semantic level of my code to be closer to what the user might report? Do you have any thoughts on that?
Yeah, it's a very valid point. And actually, I have two thoughts about this. One is that we are looking into this. So what we are looking right now is how to leverage code entities. So right now we are just using GUI elements in what I presented. Mm-hmm. Now we are trying to leverage code entities, for example, variable names, call names, method names, to actually be better in performing this mapping. So we have some evidence that this might be done. It's just we are working on it. But what you're mentioning is actually to educate or have developers semantically describe what they're doing with annotation, comments, and so on. And definitely that's something else that could be done. So something we could do, we have this technique, uses code entities. We are not yet perfect. So how we can help developers automatically add or provide incentive to add this information. So definitely that's something interesting that could be done. And then there is the dual of this. Can we help bug reporters in doing this? So providing better bug reports without actually making any additional effort in this task. And that's one of the things I wanted to talk in these two things. So I will just show a video about that. So I will skip this part as this relates to test mocking. So this is something we are about to submit to TSC. So this is a journal first paper. It will be a journal first paper, hopefully. And it's about how to help users report better bug reports. So we defined a new bug reporting system. This is called eBug. And what this eBug does is to actually, it uses different techniques to suggest steps as the user is typing the bug report, and also identify some steps which might be incomplete and complete them automatically for the users, and the user can accept these suggestions or not. And this video, so we use the static and dynamic analysis to extract information about the application. We use user profiles, so we collect some profiles from the users and then build sequences from these profiles, and then do n-gram based sequence prediction to see, as you're reporting a bug report, what is the likely next action that you might feel in the bug report, and we suggest that for you so that you might be missing this information. It makes the process more efficient and so on. And also we suggest partial sentences, and so I might say click, so type, and then immediately we prompt something that says type a certain value inside the screen. And I want to show this video, which it's kind of a demo of this system. So as of now, for let's say evaluation purposes, you select the app. This is the screen that you actually see. There are 5 portions in the screen. So I will focus on 3 of them. So the first part, you provide some general information about the bug report here. And what you have is that you put the title, some general information. Let me see if I can somehow skip to a different point. Probably I cannot, so we have to go through the video. But the idea is that, that as the user is typing the bug report, in the steps to reproduce, we provide automated suggestions on how to do that. And I generally can skip through things, but probably in this case I cannot. Let's see if how quickly we get to the point of typing the information about the bug report. So here on the right, you can see that you are displayed, you give a visual clue to the user, so to the reporter, about in which state you are reporting the information. And so this also helps making the bug reports more complete. So we think, and we found out that it does, based on some results we got. And here you can see the tool should be about to write something in the bug report. See if we have time to see that. Yes, exactly. So as the user types click, we automatically identify all the clickable elements at a certain point that could be. And here it's just an example, a tutorial on how to use this tool. And you can explore information about based on the button you're about to click, but you can, so this is an explanation on how to use the tool. The user can use this much more quickly. And so you click that, and once you actually select this element, you will see that when you say that so you type a period, this is how we detect when a sentence is complete. We actually provide an automated suggestion that, so in this case, it's saying click price per gallon text box. And let's see if we get to the point. I know we are over time. Yeah, so for example, here we suggest a complete sentence that is the next action that it should happen based on what generally users do in this case. And so we created this system and we evaluated, we have some good results on this through a user study, and people prefer to use this with respect to other systems. And also developers try to reproduce bug reports generated with this system, and they were very efficient in reproducing them. So I guess my time is over. There is a question from Girish about regarding app evolve. What happens if the change patch requires updating multiple files or classes implementation? This is a very good question. And so far we only handle intra-procedural changes. So we don't do anything inter-procedural. That's a very interesting aspect for future work to study on that. So I'm sorry I took one more minute than the time gave it to me, but if there are any questions, I am happy to stay here longer. And Sanjay, I don't know if you want to take over from here.
Sure. Thanks, Mattia. That was very engaging talk. It's good to see practical tools of testing applied to mobile apps. I think we can probably give a minute or two for any final questions, and then we can break. I think people still have some time before the next session starts for those who have classes. Any final questions? Okay, if not, again, I want to thank both Mattia and Eric for great talks this morning. And as I had announced earlier, these talks are recorded and hosted on our UMSEC channels. Thank you.
Thank you.